Quantum mechanics is the strangest and most mind-bending branch of physics. It is where the very fabric of reality behaves in ways that defy common sense. In the quantum realm, particles can be in two places at once, teleport across space through quantum entanglement, and even change their state simply by being observed. Despite its paradoxes, quantum mechanics underpins modern technology, from transistors to quantum computing. The quantum phenomenon is equally mysterious and jaw-dropping. Richard Feynman, a legendary physicist, once said, "I think I can safely say that nobody really understands quantum mechanics." But we're here to try anyways.
Welcome to the Mysteries of Quantum Mechanics Simplified, where we unravel the mysteries of the universe, one quantum puzzle at a time. It's a show where we step into the realm of the very small, where reality itself begins to behave in unexpected ways. From the birth of quantum mechanics to its strangest paradoxes, we'll explore how our understanding of physics was shattered and rebuilt. I am your host, Inara, part of the Turing's physics editorial team and self-appointed translator of physics speak into everyday language.
I'm Jessica, your guide to the quantum world. Together, we will be your host through the journey into the world of quantum mechanics. Trust us, nothing in classical physics prepares us for what quantum mechanics unravels. What better place to start this journey than the way all great revolutions do, with a crisis, a moment when the old ways of thinking no longer work. And for physics, that moment came at the dawn of the 20th century. For centuries, physics was ruled by certainty. It was an age where the laws of nature were seen as absolute, guiding everything from the fall of an apple to the motion of planets. Classical physics, as we call it today, was a grand achievement, a theory of everything known at the time.
And the theory had some heavyweight architects.
The greats such as Galileo Galilei, Johannes Kepler, or Isaac Newton. Each of them made fundamental contributions to our understanding of the universe. Galileo, in the early 17th century, championed the scientific method, refining the telescope to study celestial bodies and providing evidence that the Earth orbits the sun. His laws of motion laid the groundwork for Newton's later work. Johannes Kepler, through meticulous analysis of astronomical data, formulated the three laws of planetary motion, showing that planets move in elliptical orbits rather than perfect circles, and that their speeds vary depending on their distance from the sun. His work bridged observational astronomy and physics, paving the way for Newton. Finally, Isaac Newton unified these insights with his Principia Mathematica, formulating the three laws of motion and the universal law of gravitation, establishing the idea that the same physical laws govern both the heavens and the earth. Together, these giants of science described the world as a vast, predictable machine, where every force and every motion could be calculated with precision.
It sounds like classical mechanics left nothing to chance.
Exactly. This was the world of determinism. The universe was seen as a grand clockwork mechanism ticking in perfect order. Classical physics was incredibly successful at explaining countless natural phenomena with astonishing precision. Newton's laws predicted planetary orbits with such accuracy that they enabled the discovery of Neptune in 1846, based purely on perturbations in Uranus's motion. The laws of fluid dynamics, based on classical mechanics, helped engineers design ships and bridges, while thermodynamics explained how heat engines worked, paving the way for the Industrial Revolution. Maxwell's equations unified electricity and magnetism, leading to the advent of radio waves, electric power, and telecommunications. Every major scientific and technological breakthrough seemed to reinforce the idea that the universe operated according to unbreakable, deterministic laws. This philosophy reached its pinnacle in the 19th century with Pierre-Simon Laplace's demon.
Laplace's demon sounds ominous.
Not so much ominous as ambitious. Laplace was a French mathematician who made significant contributions to probability, astronomy, and physics. He suggested that if there were an all-knowing intelligence, which some referred to as his demon, who knew the exact position and velocity of every particle in the universe, it could calculate the entire past and future with perfect accuracy.
So, according to Laplace, the universe was just a series of dominoes, each event triggering the next, forever predictable.
Precisely. Everything from the orbits of planets to the motion of molecules followed Newtonian laws, leaving no room for randomness. This philosophy shaped science, engineering, and even our understanding of society. Industrial machines, bridges, locomotives, everything was designed under the assumption that the universe was orderly and predictable.
That's oddly comforting, knowing that the universe follows rules we can understand. So, where did it go wrong?
Well, the cracks in classical physics were subtle at first, but they grew into gaping holes. The world of the very small, the atomic and subatomic realm, did not obey Newton's laws at all. Instead, it behaved in ways that defied logic and intuition. That's when physics ran into a wall.
That sounds dramatic. What exactly happened?
The problem started with something called black body radiation. Imagine you heat up a piece of iron until it glows red, then white. Classical physics could explain why it changed color using equations based on electromagnetism and thermodynamics. The idea was that all objects emit thermal radiation, and as they get hotter, they emit more energy across a range of wavelengths. According to classical physics, this energy emission should be smooth and continuous with increasing intensity as the wavelength decreases. The theory predicted that at higher and higher frequencies, especially in the ultraviolet range, the energy emitted should keep increasing indefinitely. This meant that in theory, an object should emit an infinite amount of energy at very short wavelengths, which is clearly impossible. This absurd prediction became known as the ultraviolet catastrophe.
Infinite energy? That doesn't make any sense.
Not at all. In reality, objects do not keep emitting more and more energy at higher frequencies. Instead, the intensity of radiation peaks at a certain wavelength and then drops off at shorter wavelengths. This means that rather than producing an ever-increasing amount of ultraviolet radiation, as classical physics predicted, real black bodies exhibit a well-defined spectrum of emitted energy. Physicists observed that as temperature increased, the peak of the emitted energy shifted to shorter wavelengths, explaining why heated objects transition from red to blue as they get hotter. The experimental data showed a perfect smooth curve where energy emission peaked at a specific point and then tapered off, directly contradicting classical predictions. But at the time, classical physics had no mechanism to explain why this happened.
So physicists were stumped?
Completely. The equations they trusted, the very same equations that had successfully predicted planetary motion, the mechanics of fluids and electromagnetic waves, suddenly gave nonsensical results when applied to black body radiation. Something was missing. And then along came Max Planck. Planck wasn't looking to shake the foundations of physics. He was simply trying to fix an equation. In 1900, he found a mathematical trick that made the infinite energy problem disappear.
What sort of trick?
His trick was actually the first step toward quantum mechanics. He suggested that energy isn't emitted continuously, like classical physics assumed, but in discrete packets, quanta. This idea was radical, and Planck himself didn't fully believe it at first. But when he used this assumption, suddenly the math worked.
So instead of energy flowing out smoothly, it jumps in steps?
Yes. Think of it like climbing stairs instead of walking up a ramp. Energy can only be emitted or absorbed in these fixed amounts. This was a completely new way of thinking about nature.
And this solved the ultraviolet catastrophe?
It did. When Planck applied his idea, his equation perfectly matched experimental results. No more infinite energy predictions. But this simple fix came with an unsettling implication, one that would shake physics to its core. Even Planck himself was skeptical. He saw his equation as a useful mathematical trick, not a fundamental law of nature. To him, quantization was just a desperate attempt to fit the experimental data, nothing more. For years, he resisted the idea that nature itself might be quantized. Planck was a staunch believer in classical physics, and the notion that energy could only be exchanged in discrete packets contradicted everything he had been taught. The very idea of discontinuous energy went against the prevailing belief in smooth, predictable laws of motion and electromagnetism. But Planck had no other choice. When he applied his assumption, reluctantly, that energy could only be emitted in discrete amounts proportional to their frequency, the mathematics suddenly made perfect sense. The ultraviolet catastrophe vanished. His equation fit experimental data perfectly. He later wrote that he had introduced quantization as an act of desperation, never truly believing it would revolutionize physics. And he was not alone in his skepticism. Many of his peers dismissed the idea. The great physicists of the time, including Ludwig Boltzmann and Hendrik Lorentz, were hesitant to embrace such a radical departure from classical thinking. To them, Planck's solution was a mathematical convenience, not a real description of nature. But a few, like Einstein, saw something deeper. Just a few years later, Einstein took Planck's idea and pushed it further than anyone. He proposed that light itself is made of discrete packets, particles we now call photons. This was an even greater shock to the physics community. Planck had suggested quantization reluctantly. Einstein embraced it fully, challenging the deeply held belief that light was purely a wave. That's when physics truly started to unravel. Planck's idea solved one problem, but led to an even deeper mystery, one that would eventually give birth to quantum mechanics. The controversy that followed would divide physicists for years and set the stage for the quantum revolution.
I have a feeling things are about to get a whole lot weirder.
Oh, you have no idea. There was another puzzle, one that was just as baffling. Why do atoms emit light in specific colors? If you look at the light from the sun or a candle, it appears smooth and continuous. But if you take that light and pass it through a prism, you should get a full rainbow of colors, blending seamlessly from red to violet. That's what classical physics predicted, continuous emission. But when scientists studied the light from heated gases like hydrogen, they saw something completely different.
Different how?
Instead of a full rainbow, they saw discrete lines, sharp, isolated bands of color at specific wavelengths. No blending, no smooth transition, just specific colors appearing while others were missing entirely. This was totally unexpected. It was as if nature had imposed strict rules on how atoms could emit light.
And classical physics had no explanation for this?
Not really. According to classical physics, electrons orbit the nucleus like planets around the sun. That meant they should be able to emit energy in a continuous range, just like a vibrating string can produce different musical notes. But that's not what experiments showed. Instead, atoms seem to emit light only at very specific wavelengths, as if they were somehow quantized. Niels Bohr eventually addressed this by proposing that electrons occupy specific energy levels and can jump between them, emitting or absorbing photons of specific energies.
So physicists had an atomic model that predicted one thing and experiments showed something else entirely?
Exactly. And it got even worse. According to classical electromagnetism, orbiting electrons should constantly lose energy and spiral into the nucleus within a fraction of a second. But atoms were stable. Something was keeping electrons from collapsing into the nucleus, and classical physics had no idea why.
So with another mystery and another crack in classical physics?
Yes, the atomic spectra problem and the stability of atoms were two gaping holes in our understanding. It was becoming clear that a completely new way of thinking about physics was needed. These problems shattered the certainty of classical physics. Physicists faced a dilemma: reject the evidence or rethink reality itself. The universe was speaking, and its message was clear. Our understanding of physics was incomplete. This was the birth of quantum mechanics, a radical new framework that would soon redefine our understanding of the microscopic world.
So this was the moment when reality itself seemed to change?
Yes, enter physicists such as Max Planck, Albert Einstein, and Niels Bohr, each of whom will go on to become a legend. Each of them would play a crucial role in reshaping physics. The 20th century would become the battleground for a new war in physics, a war of ideas, of intuition against evidence, of classical certainty against quantum chaos. And it all started with Max Planck, the man who unknowingly set the revolution in motion. He would unlock a door that could never be closed, forever altering the course of science.
And where does that door lead?
The wonderful world of quantum mechanics, to a world where energy is not smooth but granular, where particles exist in multiple places at once, where certainty is replaced by probabilities. It all began with a single question. What if energy comes in packets? What if nature itself is quantized? Imagine a blacksmith's forge glowing red hot. As it gets hotter, the color shifts to yellow, then white, then blue. Classical physics predicted that as temperature increased, objects should emit more and more energy at higher frequencies. But there was a problem, an impossibility known as the ultraviolet catastrophe. As we briefly discussed in the first episode, classical physics, based on Maxwell's equations and the wave theory of light, predicted that as temperature increased, the amount of radiation emitted by a heated object should increase continuously across all frequencies. In particular, it suggested that at higher and higher frequencies, especially in the ultraviolet range, the energy output should skyrocket to infinity. This was known as the ultraviolet catastrophe, a glaring contradiction because real-world experiments showed something entirely different. Instead of an unbounded increase, radiation peaked at a certain frequency and then dropped off. The equations physicists relied on simply didn't work, exposing a fundamental flaw in classical theory.
How did they fix it?
Enter Max Planck. Planck was trying to find a mathematical solution to the ultraviolet catastrophe when he discovered something mind-blowing. Instead of treating energy as a smooth, continuous wave, he proposed that energy could only be emitted or absorbed in discrete packets, which he called quanta. This was encapsulated in his equation that introduced Planck's constant. Planck's assumption imposed a strict limit on how energy is exchanged, preventing the runaway infinity predicted by classical physics. By constraining energy to quantized steps, he successfully curved the blackbody radiation spectrum, ensuring that the total energy emitted at high frequencies would drop off, matching experimental results perfectly. This was the first clear indication that nature itself might be quantized at the most fundamental level.
So energy isn't smooth, it jumps in steps?
Exactly. Imagine climbing stairs instead of walking up a ramp. Energy could only be emitted or absorbed in specific amounts, proportional to their frequency. Planck identified a fundamental proportionality constant that determines the size of each quantum of energy in a given system. It defines the relationship between the energy of a quantum and its frequency. Higher frequency radiation carries more energy per quantum than lower frequency radiation. Think of it like musical notes. Each note on a piano corresponds to a specific frequency, and Planck's constant is like a rule that dictates that you can only play in fixed notes, not slide continuously between them. You can increase the pitch, but only in defined steps. In the same way, energy can only be transferred in specific, discrete amounts, with no in-betweens.
How was the initial reaction to the proposal?
Oh, it was utter shock. Planck himself didn't believe it at first. He saw it as a mathematical trick, not a real physical property. He spent years trying to reinterpret his own equation in a way that would fit classical physics. But the universe didn't care about his discomfort. The numbers were clear, energy was quantized, and then came along Einstein. One of the biggest mysteries at the time was the photoelectric effect. Scientists had observed that shining light on metal could eject electrons, but the behavior of these ejected electrons was perplexing. Classical physics predicted that increasing the brightness of the light should transfer more energy to the electrons, causing them to be ejected with greater kinetic energy. However, experiments showed something entirely different. Only light above a certain threshold frequency could eject electrons, no matter how intense the light was. Even dim ultraviolet light could dislodge electrons, while the brightest red light had no effect at all. This contradicted the wave theory of light, which assumed that energy was spread evenly over the wave and could be gradually accumulated by electrons. Clearly, something fundamental about light and energy was missing from classical physics.
When we say light is intense or dim, what does that actually mean? How do we define intensity?
Great question. So, in classical physics, intensity refers to the total amount of energy carried by the light wave. It's related to the amplitude of the wave. The bigger the wave, the more intense the light. Classical physics assumed that a more intense light wave should transfer more energy to electrons, causing them to be ejected with greater kinetic energy. But the photoelectric effect didn't follow that rule. Only the frequency mattered, not the intensity. This was a huge shock to physicists.
I see the challenge. Shouldn't more light mean more energy?
It should if light were a continuous wave. But in 1905, Albert Einstein took Planck's quantum idea and made a daring leap. Light itself is made of particles, photons. Einstein proposed that instead of being a smooth wave, light was a stream of discrete packets of energy. His inspiration came from Planck's idea that energy could only be emitted or absorbed in specific amounts. He took this one step further and suggested that light itself was made up of these packets. Einstein's breakthrough was rooted in an attempt to explain the photoelectric effect in a way that classical physics simply could not. He reasoned that if light were composed of individual photons, then each photon would transfer its energy all at once to an electron in the metal. The energy of a single photon would be determined by the frequency of the light. Higher frequency light carried more energy per photon. This elegantly explained why increasing brightness or adding more photons didn't make electrons more energetic, but increasing the frequency did. If a photon didn't have enough energy to free an electron, no amount of additional photons could make up for it. As experimental evidence mounted, Einstein's photon hypothesis became one of the cornerstones of quantum mechanics.
Yeah, it sounds radical.
It was. The physics community was full of skepticism. Many physicists, such as Robert Millikan, were skeptical and sought to disprove the idea through meticulous experiments. However, Millikan's own work on the photoelectric effect in 1916 ended up confirming Einstein's predictions exactly. This was a turning point, but skepticism still lingered. The decisive moment came in 1923, when Arthur Compton demonstrated that X-rays scattered off electrons in a way that could only be explained if light behaved as discrete particles, photons. This provided irrefutable evidence for Einstein's theory and marked the beginning of the widespread acceptance of quantum ideas. By 1926, quantum mechanics was beginning to take shape as a formal framework, and Einstein's once radical hypothesis became one of its foundational pillars.
Wait. If photons weren't conclusively proven until 1923, why did Einstein receive the Nobel Prize for them in 1921? Wasn't that premature?
Einstein had already come to be recognized as one of the world's brightest minds by then. His work on special and general relativity was seminal. The Nobel Committee was, however, hesitant to award Einstein the prize for relativity because it was still controversial. Instead, they chose to recognize his work on the photoelectric effect because even though many physicists remained skeptical of photons, the equation he derived perfectly explained the experimental results. In essence, his model worked so well that it couldn't be ignored. Even if not everyone fully accepted its implications at the time, the prize citation even carefully avoided mentioning photons explicitly, focusing instead on the discovery of the law of the photoelectric effect. It wasn't until later, with experiments like Compton's, that the reality of photons became undeniable.
So Planck quantized energy, Einstein quantized light. The foundations of classical physics were crumbling. Where does our story lead us next?
Our story is about to get weirder as we reach the cusp of the birth of quantum mechanics as a complete theory. Niels Bohr, the Danish physicist, introduced a revolutionary model of the atom, where electrons could only occupy specific orbits, solving the mystery of atomic spectra. Werner Heisenberg, the German physicist, formulated the uncertainty principle, proving that the very act of measurement imposes fundamental limits on what we can know. Erwin Schrödinger, the Austrian physicist, developed wave mechanics and his famous equation, revealing that electrons behave not as particles, but as strange probability waves. A universe where particles seem to disappear and reappear without ever crossing the space between, and where the very rules of cause and effect begin to blur. What is holding atoms together? What prevents them from collapsing? Buckle up for the roller coaster ahead. Let's go back to the early 20th century. In 1911, Ernest Rutherford and his team at Manchester conducted an experiment that would change our understanding of the atom forever, the gold foil experiment. They fired tiny alpha particles, positively charged helium nuclei composed of 2 protons and 2 neutrons, at a thin sheet of gold foil, expecting them to pass straight through based on the prevailing plum pudding model, which assumed that atoms consisted of diffuse positive charge embedded with electrons. Instead, what they saw was shocking. While most particles did pass through, some were deflected at large angles, and a few even bounced straight back. This led Rutherford to a radical conclusion. The atom was mostly empty space, with a tiny, dense, positively charged nucleus at its center where nearly all its mass was concentrated. Electrons, he proposed, must orbit this nucleus at a distance, much like planets orbiting the sun. This model revolutionized atomic physics, but came with a troubling flaw.
What kind of flaw?
Rutherford's model suggested that electrons orbit the nucleus like planets around the sun. However, according to classical electromagnetism, a charged particle moving in a circular orbit, like an electron, should constantly emit electromagnetic radiation. As it radiates energy, it should lose momentum and spiral inward, collapsing into the nucleus in less than a millionth of a second. This posed a fundamental problem. If this were true, atoms couldn't exist as stable structures, yet clearly they do.
But atoms don't collapse like that.
Exactly. Atoms are stable, yet Rutherford's model couldn't explain why. It was a major crisis in physics. Enter Niels Bohr, a young Danish physicist who had just arrived at Rutherford's lab in Manchester. Bohr came from an intellectual background. His father, Christian Bohr, was a renowned professor of physiology, and his home was a gathering place for some of Denmark's brightest minds. Young Niels absorbed complex ideas at an early age, but remained humble and introspective, never seeking the limelight. As a young scientist, he faced early setbacks. When he went to Cambridge to work under J.J. Thomson, the discoverer of the electron, he was largely dismissed. Thomson found Bohr's approach unconventional, and Bohr struggled to fit into the rigid research environment. Disappointed but undeterred, he found his true intellectual home with Ernest Rutherford in Manchester. Rutherford, unlike Thomson, recognized Bohr's brilliance and encouraged his independent thinking. For Bohr, taking all of these ideas into account made a bold leap, one that would redefine our understanding of the atom. Instead of continuous orbits, he proposed that electrons could only occupy fixed energy levels, what we now call quantized orbits.
So electrons weren't free to move however they wanted, as we had initially expected.
No, Bohr's key insight was that electrons could only exist in these stationary states, each corresponding to a specific energy. And when an electron changed levels, it had to jump between them, emitting or absorbing energy in discrete packets we know as photons. Bohr's journey toward quantum mechanics was not an easy one. At first, he explored classical atomic models, but they failed to explain experimental observations. One early attempt to incorporate quantum ideas came from Arthur Erich Haas in 1910, who suggested that the size of an atom could be derived using Planck's constant. However, his work was largely ignored. The turning point came when Bohr recognized that classical electromagnetism could not account for atomic spectra. At the 1911 Solvay conference, leading physicists debated the growing evidence that classical mechanics was incomplete. Bohr, influenced by these debates and discussions with Rutherford, made the bold leap and proposed his framework. The realization that electrons could only exist in discrete energy levels and transition between them by absorbing or emitting photons was revolutionary. It was an intellectual risk that defied centuries of classical physics, but it would soon prove to be one of the most profound breakthroughs in modern science.
And this explained atomic stability?
Yes, electrons in a quantized orbit wouldn't radiate energy continuously. They were stable, locked into their energy levels until something caused them to transition.
But how do we know Bohr was right?
The answer lay in a decades-old mystery, the hydrogen spectrum. When heated, hydrogen doesn't produce a continuous spectrum, it emits sharp, distinct lines. This baffled physicists for years. Classical physics predicted that atoms should emit a continuous range of colors, much like sunlight passing through a prism. Instead, when scientists analyzed the light emitted by heated hydrogen gas, they found only specific, isolated colors, bright lines appearing at precise wavelengths, forming what became known as the Balmer series. This was a major mystery. If electrons were free to orbit the nucleus in any way, why weren't they emitting all possible wavelengths of light? Why were only certain colors appearing? The answer, as Bohr proposed, lay in the concept of quantized energy levels. Electrons could only exist at specific orbits, and transitions between these orbits dictated the precise energy and therefore wavelength of the emitted light. Bohr's model not only explained these missing colors, but also provided a mathematical foundation that perfectly matched the observed hydrogen spectrum. His work on atomic structure quickly gained recognition, and he won the Nobel Prize in 1922, a year after Einstein won the same for explaining the photoelectric effect.
Does Bohr's model on atomic structure still stand today?
Not quite. While it worked beautifully for hydrogen, it failed for multi-electron atoms. It also couldn't explain the fine structure of spectral lines or the newly discovered electron spin. Even Bohr himself was uneasy about the limitations of his model. He had taken a bold step in introducing quantum ideas, but deep down he knew his model was incomplete. He struggled with the nature of quantum jumps. Were electrons really teleporting between orbits, or was something deeper at play? He wasn't fully convinced that his own mathematical framework reflected the full reality of atomic structure. As experiments pushed further, cracks began to show. The introduction of the Zeeman effect, where spectral lines split in a magnetic field, suggested that electrons had an additional property, something that Bohr's model couldn't account for. Scientists like Wolfgang Pauli and Arnold Sommerfeld expanded upon his ideas, introducing concepts like electron spin and elliptical orbits. But even these refinements weren't enough.
So what happened next?
Bohr, rather than resisting, embraced the challenges. He encouraged the next generation of physicists, Heisenberg, Schrödinger, and Dirac, to push beyond his model. He believed science should evolve, and when quantum mechanics did just that, he championed its new, unsettling vision of reality. A more complete quantum theory was needed. This led to the development of Schrödinger's wave mechanics and Heisenberg's matrix mechanics, which replaced neat electron orbits with the concept of probability clouds.
Sounds like quantum mechanics has started to become weirder.
Bohr's model set the stage, but it raised even deeper questions. Before we dive into the quantum madness, let's start with how the world was supposed to work. For centuries, physics classified everything into two categories: waves and particles.
So waves are things like water ripples, and particles are like grains of sand, right?
Exactly. Waves are disturbances that travel through a medium, carrying energy without carrying matter. They spread out, interfere, and overlap. Think of ocean waves passing through a narrow gap and forming patterns. Sound waves travel through air by compressing and expanding particles, creating pressure variations that we hear as sound. Light waves, on the other hand, can travel through empty space, oscillating as electromagnetic fields. Waves also exhibit a fascinating property called interference. When two waves meet, their peaks and troughs can either amplify each other, forming constructive interference, or cancel each other out, leading to destructive interference. This behavior is key to understanding the double-slit experiment, where light and even particles like electrons behave in ways that defy classical intuition. Particles, on the other hand, are discrete objects. They have a definite position and move in well-defined paths following Newton's laws of motion. Think of a baseball flying through the air. It follows a predictable trajectory based on its initial velocity and the forces acting upon it. Unlike waves, particles do not spread out or overlap. They exist as singular entities at specific locations.
And for the longest time, scientists thought these were completely separate things, I suppose.
That's right. It was Newton versus Huygens. Newton championed light as particles, while Huygens argued for light as waves. By the early 1800s, Thomas Young provided strong evidence in the debate with his famous double-slit experiment. Or at least that's what we thought. In 1801, Thomas Young devised a simple but brilliant experiment. Imagine you have a handful of baseballs and two narrow slits in a wall. If you throw the baseballs at the slits, each should go through one slit or the other, landing in two neat piles on the other side. Simple, right? Now, imagine instead that you drop two pebbles into a pond at the same time. The ripples spread outward and overlap, creating a pattern of peaks and troughs. This is interference, a signature of wave behavior.
So if light was just a stream of particles, it should behave predictably with two bright spots where the light passed through the slits. But if light was truly a wave, then something else, something stranger, I suppose, should happen. So what was the verdict?
Thomas Young, an English scientist, designed an experiment to settle the debate about the nature of light. He set up a barrier with two narrow slits and a screen behind it. Then he shined light through the slits, expecting to determine whether light behaved as particles or waves. If light were made of particles, we should see two distinct bands where the light passed through the slits. But instead, Young saw something completely different, an interference pattern. Just like waves, the light was spreading out and interfering with itself, forming alternating bright and dark regions on the screen. The bright areas corresponded to where the waves reinforced each other, called constructive interference, while the dark areas appeared where waves canceled each other out, called destructive interference. This pattern could only mean one thing. Light was not made of tiny particles traveling in straight lines, but instead behaved like a wave, spreading out and interacting with itself in a way that defied classical intuition.
So this proved that light was a wave?
That's what scientists thought for over 100 years. Young's experiment seemed to prove beyond doubt that light was a wave. No one questioned it. At the time, many scientists believed light waves needed a medium to travel through called the luminiferous aether. This idea persisted for decades until the Michelson-Morley experiment in 1887 found no evidence of such a medium. This unexpected result set the stage for Einstein's theory of relativity, proving that light needed no medium at all. But the real shock came when physicists decided to revisit Young's experiment, not with light, but with electrons. In the 20th century, scientists decided to fire individual electrons through the slits. Since electrons are particles, they expected to see two distinct spots on the screen. But when they checked the results, they found something shocking.
Let me guess. They saw an interference pattern, just like waves.
Exactly. This was baffling because all our earlier experiments had confirmed that electrons behaved as particles. When we measured them in other experiments, they landed in precise locations, had well-defined momenta, and obeyed Newtonian mechanics. But here, they were behaving as if they were waves, spreading out and interfering with themselves. This is similar to the nature of light itself. For centuries, scientists debated whether light was a wave or a particle. Young's double-slit experiment had shown that light was a wave, but later experiments, like the photoelectric effect explained by Einstein, demonstrated that light was also made of photons, particles of energy. Now, electrons, previously thought of as particles, were behaving like waves. This led to a shocking realization. Perhaps everything at the quantum scale exhibited both particle and wave behavior, depending on how we observed it.
But that makes no sense. How can a single electron go through both slits? Can't we just place some kind of camera or detector at the slits to see which path the electron takes?
That's what scientists did. The electron seemed to exist in multiple paths simultaneously. until we decided to observe it. That's where things get even stranger. When scientists placed a detector at the slits to see which path the electron took, the interference pattern vanished. The electron behaved like a normal particle again. This baffled physicists. Why would merely observing the electron force it to choose a single path? This sparked a heated debate about the very nature of reality. Physicists like Niels Bohr and Werner Heisenberg argued that measurement itself alters the quantum state, a key idea in the Copenhagen interpretation. This means that an interaction with any measuring device, not necessarily a conscious observer, determines the outcome. Meanwhile, Albert Einstein famously pushed back, believing that quantum mechanics was incomplete, famously stating, "God does not play dice with the universe." This experiment led to groundbreaking discussions on quantum measurement, probability, and the idea that particles do not have definite properties until measured. It paved the way for concepts like quantum entanglement and the many worlds interpretation, where every possible outcome exists in parallel realities.
But what does this mean? Did the electron know it was being watched? And if so, does reality itself depend on observation? How can just looking at something change its behavior? Sounds like that's what my dog would do, but not the electrons.
These questions remain at the heart of quantum mechanics, and we still don't have all the answers. Before we measure an electron, it behaves as if it's in multiple places at once, existing in a strange state of probability. But the moment we observe it, it chooses a single position. This is called the observer effect, and it suggests that at the quantum level, reality is not fixed until it is measured. Variations of classic double-slit experiments have shown that even future observations can retroactively determine whether an electron behaved like a wave or a particle. In the 1999 quantum eraser experiment by Yoon-Ho Kim and others, scientists used entangled photons in a delayed choice setup. The decision to measure one photon's path affected its entangled twin, even after it had already passed through the slits. How exactly this happens is still a mystery, but in the coming episodes, we'll dive deeper into quantum superposition and Schrödinger's famous thought experiment to illustrate this paradox.
So what does this mean for the real world? If an electron can be in two places at once, what about bigger things like entire objects or even people?
That's a natural question. Quantum effects usually stay at the atomic level. But experiments have shown that even large molecules can exhibit wave-like behavior. Double-slit experiments with C60 fullerenes, buckyballs, which are soccer ball-shaped molecules consisting of 60 carbon atoms, still produced an interference pattern, proving that wave-particle duality persists even at relatively large scales. More recently, researchers have extended these experiments to organic molecules containing up to 2,000 atoms. These massive molecules also displayed wave-like properties under highly controlled conditions, suggesting that quantum effects might persist far beyond the atomic scale. This raises an even bigger question. If electrons and large molecules can behave as both waves and particles, does this apply to everything? What about objects in our daily lives? Cars, tennis balls, or even humans? Theoretically, everything has a wavelength, as described by de Broglie's equation, which relates an object's wavelength to its momentum. However, for larger objects, the wavelengths become so incredibly tiny that any wave-like behavior is undetectable. A tennis ball, for example, has a wavelength so small that it is completely negligible, meaning we only observe it as a particle. This happens because macroscopic objects interact with their environment constantly, causing a process called decoherence, which destroys quantum superpositions. Unlike isolated quantum particles, larger objects are constantly measured by their surroundings: air molecules, photons, thermal vibrations, forcing them into a definite state and preventing interference effect. So while everything technically has a wave nature, quantum effects become invisible at larger scales, keeping the classical world intact.
Has wave-particle duality been tapped for any practical applications?
For sure, wave-particle duality is already shaping the world around us. One of the best examples is electron microscopy. Since electrons exhibit wave behavior, we can use electron diffraction to image objects at an atomic scale, allowing us to see details far smaller than traditional light-based microscopes. Then there's quantum computing, which relies on superposition and wave-like probability distributions to perform calculations far beyond the reach of classical computers. Another key application is interferometry and precision measurement, used in projects like LIGO, which detects gravitational waves, ripples in spacetime itself by exploiting wave interference. In the realm of materials science, wave-based nanotechnology is unlocking new ways to manipulate matter, using quantum wave properties to engineer revolutionary materials at the smallest scales.
Wow, this is a lot to think through. So where are we headed next?
Imagine you're holding your phone right now. You know exactly where it is, right? But at the quantum level, knowing the exact position of an object means you cannot know where it is going. And the more accurately you measure its motion, the fuzzier its location becomes. This is the Heisenberg uncertainty principle. Imagine trying to take a perfectly sharp photograph of a car at night. The moment you adjust your camera to capture it precisely, the motion becomes a blur. But if you set the camera to track its speed, the car itself becomes indistinct, smeared across the image. This paradox hints at a fundamental truth of quantum mechanics. The more precisely we measure a particle's position, the less we can know about its momentum. And this uncertainty extends to other quantum properties, like energy and time. It's not a failure of our instruments, it's a fundamental feature of reality itself. Welcome to the world of quantum uncertainty. For centuries, we thought the universe was predictable. Newton's laws gave us a way to determine where something was, where it was going, and how fast it was moving, if we just had enough information.
So if I throw a baseball, classical physics says we can calculate exactly where it will land?
Exactly. But with the discoveries by Einstein, Bohr, and others, things started to change. Bohr's atomic model revealed that electrons don't follow classical orbits like planets, but instead jump between discrete energy levels. And then came Heisenberg, who found something even more profound. Werner Heisenberg was a young German physicist, part of a generation that sought to reconcile the growing paradoxes of quantum mechanics. In the 1920s, he was working under Niels Bohr, trying to refine our understanding of atomic structure. Inspired by the work of Bohr and Einstein, Heisenberg realized that electrons could not be described with classical certainty. Something deeper was at play. Heisenberg's uncertainty principle states that a particle's position and momentum cannot both be precisely known, because at the quantum level, these properties are not simultaneously well defined. This insight led Heisenberg to formulate his famous uncertainty principle, the realization that the more precisely we measure one conjugate variable of a particle, the less we can know about the other. These pairs are energy and time, or position and momentum. It wasn't just a limitation of our tools, but a fundamental feature of reality itself.
So what does this actually mean? Does it mean that laws of universe doesn't let us fully know both where something is and how fast it's moving?
For one, it explains why electrons don't spiral into the nucleus. Electrons exist in a superposition of possible positions, described by a wave function. Instead of fixed orbits, we get probability clouds, known as electron orbitals, where electrons are most likely to be found. This idea comes from the realization that electrons don't travel in neat circular paths around the nucleus like planets around the sun. Instead, they behave like waves, existing in a spread-out region of space rather than a single defined point. These orbitals represent regions of probability, meaning we can only predict where an electron is likely to be found, not its exact location. The denser regions of the probability cloud indicate where the electron is most likely to be detected, while the less dense regions mean a lower probability.
That's difficult to wrap your head around. So uncertainty isn't just a measurement issue. It's a fundamental part of reality.
Exactly. It's not that our instruments aren't good enough. the universe itself doesn't allow perfect knowledge. And this brings us to one of the most well-known thought experiments in physics, Schrödinger's cat. This thought experiment has become a staple of popular science discussions, referenced in books, movies, and TV shows as a metaphor for uncertainty and paradox. What started as a critique of quantum mechanics has since evolved into a symbol of the mysteries of the quantum world.
Oh, Schrödinger's cat. I remember first hearing about it in a Big Bang Theory episode. Sheldon used it to help with Penny's love problems.
Right, so Schrödinger proposed this thought experiment to illustrate the odd nature of quantum mechanics. Imagine placing a cat inside a sealed box, along with a radioactive atom, a Geiger counter, and a vial of poison. In this scenario, the atom has a 50% chance of decaying within a certain time frame. If it decays, the Geiger counter detects it, triggering the release of poison and resulting in the cat's death. If the atom does not decay, the poison is not released, and the cat remains alive. According to the Copenhagen interpretation of quantum mechanics, until we observe the system, the atom is in a superposition of decayed and not decayed states, meaning the cat's fate is also undefined until measurement occurs. This challenges our understanding of reality. Does the act of measurement determine what is real, or was the cat always in one definite state? If the atom decays, the counter triggers a hammer, shattering a vial of poison. The fate of the cat hinges on the unpredictable quantum world.
That sounds like reality only happens when we check. Is that the way to interpret it?
It's a debated topic. There are multiple interpretations. The Copenhagen interpretation, proposed by Niels Bohr and Werner Heisenberg, suggests that before measurement, a quantum system exists in a superposition of all possible outcomes. The moment we observe it, the wave function collapses, and we get a definite result. One of the most famous alternatives is the many worlds interpretation, proposed by Hugh Everett in 1957. According to the many worlds interpretation, all possible outcomes of a quantum event exist simultaneously, but in separate, non-communicating branches of the universe. In the case of Schrödinger's cat, there would be one branch where the cat is alive and another where it is dead. Both outcomes exist simultaneously, but in different branches of the universe.
So every time a quantum event happens, the universe splits? Does that would imply infinite universes, or?
This does raise an astonishing question. Does this imply an infinite number of universes, each representing every possible quantum outcome? According to this interpretation, every decision, every particle interaction, and every quantum event creates a branching of reality. Some physicists embrace this view, suggesting that we live in just one of countless diverging timelines. Others argue that this interpretation stretches quantum mechanics beyond what we can ever test. The truth is that we simply don't know. And then there's pilot wave theory, developed by Louis de Broglie and later expanded by David Bohm. This theory suggests that particles always have definite positions, guided by an unseen wave. Unlike other interpretations, it preserves determinism and avoids wave function collapse.
That sounds almost classical, like the particles are just following hidden rules.
Exactly. It tries to bring determinism back to quantum mechanics. But there's also quantum Bayesianism, or cubism, which argues that the wave function doesn't describe reality itself, but rather our knowledge and expectations about it. It treats quantum probabilities as subjective, shaped by what we know. The reality is, we just don't know. No experiment has definitively proven one interpretation over the others. But what we do know is that measurement plays a central role in quantum mechanics, and understanding it might be key to unlocking even deeper mysteries of the universe. As these ideas spread, some of the greatest minds in physics couldn't agree on what quantum mechanics really meant. One physicist insisted reality was deterministic, while another argued that uncertainty was fundamental. As quantum mechanics was being developed through new discoveries in the early 20th century, one problem lingered. The math was fine, and the equations worked, predicting outcomes with incredible accuracy. The problem, however, was what did these equations actually mean? Unlike classical physics, where reality is intuitive and predictable, quantum mechanics tells us something deeply unsettling. Particles can be in multiple places at once, measurement affects reality, and entangled particles share non-local correlations, defying classical expectations. But what does this mean? Does this mean the reality is fundamentally random, or are we simply missing a deeper layer of physics? The interpretation of quantum mechanics influences how we think about the universe itself. Are we passive observers? Are we active participants? Does reality exist independently of us, or do we bring it into existence by looking at it? This is why interpretation matters, and no debate in the history of physics has been as fierce or as consequential as the one between Albert Einstein and Niels Bohr. Let's dive in. In 1927, at the historic Solvay Conference, some of the greatest physicists of all time gathered in Brussels to discuss quantum mechanics. This included Albert Einstein and Niels Bohr. This conference marked the beginning of a legendary debate between Einstein and Bohr, one that would continue for decades. Einstein was deeply unsettled by quantum mechanics. He had spent his life uncovering the deep, beautiful laws of nature, laws that were absolute, governed by strict causality. But quantum mechanics seemed to say something different, that particles existed in a state of limbo until observed, and that reality itself was uncertain. Einstein hated this idea. God does not play dice with the universe, he famously said. Bohr, on the other hand, believed that quantum mechanics was complete. He argued that reality was not an independent thing that existed before measurement. Rather, it came into existence through measurement. To Bohr, quantum mechanics wasn't about finding an underlying hidden reality. It was about predicting what we see when we measure it. Einstein's famous remark, "God does not play dice with the universe," was met with an equally famous response from Bohr. Einstein stopped telling God what to do with his dice. This encapsulated the fundamental divide between them. Bohr embraced probability and uncertainty, while Einstein insisted on an underlying determinism.
So Bohr was saying that reality doesn't exist until we look at it?
Precisely. According to Bohr, asking where an electron is before we measure it is meaningless because without measurement there is no is. Einstein responded with thought experiments. One of the most famous was the EPR paradox in 1935. Einstein, along with Podolsky and Rosen, proposed a scenario where two entangled particles could instantly affect each other, no matter how far apart they were. This was spooky action at a distance, as Einstein called it, suggesting that either quantum mechanics was incomplete or something faster than light was carrying information.
Did Bohr have an answer?
It did, but it wasn't a straightforward one. Bohr argued that even though the particles seemed to influence each other instantly, there was no actual faster-than-light signal being transmitted. Instead, quantum mechanics simply doesn't work the way classical intuition expects it to. This argument split the physics community. Scientists like Werner Heisenberg and Max Born sided with Bohr, emphasizing the probabilistic nature of quantum mechanics and the necessity of measurement in defining reality. They argued that the formalism of quantum mechanics worked perfectly, and that searching for deeper hidden variables was unnecessary. On the other hand, Einstein found allies in Erwin Schrödinger and Louis de Broglie, who were also dissatisfied with the idea of reality being observer-dependent. Schrödinger, famous for his cat paradox, argued that quantum mechanics must be incomplete if it suggested that an object could be in two contradictory states simultaneously. De Broglie, meanwhile, proposed an alternative explanation, pilot wave theory, where particles had definite positions and were guided by an unseen wave, rejecting the need for wave function collapse. Despite Bohr's rebuttals, Einstein remained unconvinced for the rest of his life. The debate was never conclusively settled during their lifetimes, but it set the stage for the later experimental tests that would either confirm or refute their positions. in 1964 when physicist John Bell came up with a way to test it. Bell's theorem mathematically showed that if hidden variables existed, if quantum mechanics was incomplete, then certain experiments should reveal it. But if Bohr was right, the results would defy classical physics.
And when the experiments were done?
Quantum mechanics won. In the 1980s, Elaine Aspect conducted experiments that violated Bell's inequality, proving that there are no hidden variables in quantum mechanics. The universe is fundamentally random at the quantum level. Einstein was wrong.
Bohr was right.
Not necessarily. Bohr's view, known as the Copenhagen interpretation, became the most accepted. But others weren't convinced. The question of how should we interpret quantum mechanics remains open. The Copenhagen interpretation is perhaps the most famous interpretation of quantum mechanics. Bohr and Heisenberg argued that the equations of quantum mechanics don't describe what is happening to a particle, but rather what we can know about it. In other words, reality isn't a definite thing until we measure it. According to Bohr, a particle doesn't have a definite position or state until it's observed. Before measurement, a quantum system exists in a superposition, a blend of all possible outcomes. The moment you measure it, the wave function collapses and one reality is chosen.
But that means the universe isn't as concrete as we thought.
Many physicists find it troubling that reality depends on an observer. Schrödinger's famous thought experiment with a cat, alive and dead at the same time, was designed to highlight this absurdity. Others argue that wave function collapse is a mysterious, unproven process. But despite its oddness, the Copenhagen interpretation remains the dominant view in quantum mechanics today.
So if the Copenhagen interpretation says that reality only becomes definite when we measure it, are there any alternative explanations?
Hugh Everett came up with an alternative and radical proposal, the many worlds interpretation. Everett argued that there's no such thing as wave function collapse. Instead, every time a quantum choice is made, the universe splits. Each possibility happens, but in separate parallel worlds. Every quantum event leads to a branching of reality, where all outcomes occur in different branches. You don't just observe a single reality, you become entangled with the outcome you measure, while another version of you experiences a different one.
That's mind-blowing, but how does that explain measurement?
Everett's idea removes the need for a special observer or collapse. Instead, all possibilities simply evolve according to Schrödinger's equation, with no exceptions. It's quantum mechanics taken literally. However, it remains controversial. While it mathematically fits quantum mechanics, it does not yet explain why we perceive one outcome instead of all possible realities. The biggest problem, however, is that it predicts an infinite number of parallel universes, but we have no way to test or interact with them. You can argue that it's a beautiful idea, but without experimental proof, it remains speculative. Another interpretation came from Louis de Broglie and later David Bohm. Unlike Bohr or Everett, de Broglie and Bohm believed that particles have definite positions at all times, even before measurement. Instead of collapsing waves or splitting universes, they suggested an invisible pilot wave that guides particles, like a hidden hand shaping their motion.
So the randomness in quantum mechanics isn't real?
Exactly. In this view, what seems like randomness is just our ignorance of the hidden variables controlling the particles. The uncertainty is an illusion. If we knew all the hidden details, we could predict everything precisely.
It sounds a lot like what Einstein wanted, an objective reality. Why didn't this idea take over?
Because while it does restore determinism, it also introduces something equally bizarre: non-locality. To work, the pilot wave must instantaneously influence particles across vast distances, even faster than light. This clashes with relativity, making many physicists uneasy.
So if Copenhagen says reality depends on observation, many worlds says everything happens, and pilot wave says everything is already determined, how do they compare?
Each interpretation has its strengths and weaknesses. Copenhagen is practical and widely used, but it's philosophically unsettling. Many worlds is elegant but untestable. Pilot Wave offers determinism but requires spooky connections across space. And the truth? We still don't know which, if any, is correct.
So after all this, we still don't know what quantum mechanics means?
Not definitively. Some more recent, newer interpretations have also been proposed. For example, could quantum mechanics itself be an emergent phenomenon, just one layer of a deeper reality? That's where emergent objective reality comes in. This is a relatively new idea that suggests quantum mechanics is not fundamental, but rather an emergent property of a deeper underlying theory of physics. Think of it like temperature. You can describe heat without knowing about individual atoms, but at a microscopic level, those atoms create temperature.
So quantum mechanics is like the surface of a deeper reality we don't fully understand yet?
Exactly. Some researchers, like Sean Carroll and Wojciech Zurek, argue that quantum behavior might emerge from deeper physical laws that we just haven't uncovered yet. Instead of wave function collapse being a fundamental rule, it could be the result of a yet unknown interaction between quantum and classical physics.
So we have equations that work. We have technology that relies on quantum mechanics. But after a century of debate, do we understand what it's telling us?
That is the open question. Quantum mechanics is true, but what it means for reality, whether the universe is local, whether parallel worlds exist, whether we shape reality by observing it, remains unresolved. Or perhaps quantum mechanics is pointing us toward an even deeper mystery, one we have yet to unravel.
So if we still don't fully understand what quantum mechanics means, how are we using it to build the future?
Well, because we have gotten good at predicting quantum outcomes, the uncertainty of quantum mechanics doesn't stop us from developing revolutionary technology, lasers, semiconductors, even quantum computing. In fact, some of the most advanced technologies today rely on quantum principles we don't yet fully grasp.
Wait, so we've built an entire technological revolution on ideas we still debate?
Well, yes, sort of. Back in the early 20th century, quantum mechanics was the theoretical playground for physicists. But as we explored this microscopic world, we started to understand how nature's fundamental rules could be harnessed. Today, we exist in a world where quantum mechanics is the silent architect of many of the technological marvels. From the precision of lasers and the computational power of semiconductors to the life-saving imaging of MRI machines, quantum physics enables many of the modern world's most important innovations. Every time you use your phone, browse the internet, or undergo a medical scan, you are witnessing quantum mechanics in action.
So how does this deep and often counterintuitive science translate into these groundbreaking applications?
To answer that, let's start with one of the most important inventions of the modern world, the semiconductor. Every digital device today, your phone, laptop, relies on semiconductors, which are the backbone of modern technology. In fact, semiconductors are the third most traded good in the world after oil and cars, with global trade exceeding $600 billion last year as per Gartner, a consultancy. But beneath the surface of every microchip, quantum mechanics is shaping the way our world operates. At the core of semiconductors is band gap theory, which explains why some materials conduct electricity while others insulate. Quantum mechanics allows us to manipulate these properties, enabling the development of transistors, the fundamental units of modern electronics. One crucial quantum phenomenon in semiconductors is quantum tunneling, where electrons pass through energy barriers that classical physics says should be impassable. This effect is key in modern microprocessors, where transistors operate at nanometer scales, allowing billions of them to be packed into a single chip. Furthermore, quantum confinement explains why nanostructures like quantum dots exhibit unique electronic and optical properties. These structures are paving the way for advanced display technologies, highly efficient solar cells, and quantum computers. Without our understanding of quantum mechanics, the technological marvels we take for granted, from microchips that power our digital age to artificial intelligence and the cutting-edge future of computing, would be impossible.
It's incredible. So quantum physics doesn't just describe the world, it lets us control it.
For sure, one of the best examples of control? Lasers. Lasers are everywhere. Barcode scanners, medical surgery, fiber optic internet. But at their core, lasers rely on quantum mechanics.
So what makes them quantum?
The key is stimulated emission, a concept first proposed by Einstein. Atoms absorb energy and their electrons jump to higher energy levels, but when they fall back down, they emit photons, particles of light. Normally, this happens randomly, but in a laser, one photon stimulates another in a carefully controlled environment, amplifying the light in a highly organized manner. This control is achieved through the use of mirrors and optical cavities, which ensure that photons bounce back and forth, aligning their phase and direction. The result is a coherent, monochromatic, and highly directional beam of light, qualities that make lasers indispensable for a wide range of applications. Lasers have become ubiquitous due to their versatility. They power fiber optic communication, enabling high-speed internet. They are used in surgery for precision cutting and in industrial manufacturing for welding and engraving. From barcode scanners in supermarkets to the most advanced space exploration tools, lasers have revolutionized countless industries, all thanks to the fundamental principles of quantum mechanics.
So quantum physics lets us create light in an ultra-precise way?
Exactly. And that same level of precision is why quantum mechanics has transformed medicine, most famously in MRI machines. If you've ever had an MRI scan, you've experienced quantum physics in action. MRI, magnetic resonance imaging, works by manipulating quantum spins in your body.
Spins, like tiny magnets?
Exactly. Your body is full of hydrogen atoms, and each hydrogen nucleus behaves like a tiny quantum magnet due to a property called spin angular momentum. MRI machines take advantage of this quantum spin by applying a strong external magnetic field, which forces these tiny magnets to align either with or against the field, a quantum state known as Zeeman splitting. Once aligned, the machine sends radio frequency pulses that briefly tip the hydrogen nuclei out of alignment. When the RF pulse is turned off, these nuclei relax back to their original positions, releasing energy in the process. This released energy is detected by the MRI machine and is used to construct highly detailed images of tissues inside the body. Because different tissues contain varying amounts of hydrogen fat, muscle, and tumors, for example, MRI can distinguish between them based on their unique relaxation times. Advanced techniques like functional MRI go even further, tracking blood flow changes to map brain activity in real time.
So without quantum mechanics, MRI scans wouldn't exist?
Not really, and in the future, quantum technology could lead to even more breakthroughs, like quantum-enhanced imaging that could detect diseases earlier than ever. We've only scratched the surface of what quantum mechanics can do. The next big leap is in quantum computing. Unlike classical computers, which use bits that are either 0 or 1, quantum computers use qubits, which can exist in a superposition of both states simultaneously. When measured, they collapse into a definite state. This principle, combined with entanglement and quantum interference, allows quantum computers to process vast amounts of data in parallel, unlocking computational power far beyond classical limits. However, there are still major challenges, such as quantum decoherence, where fragile quantum states are disrupted by their environment. Researchers are working on error correction techniques and more stable qubit designs, including superconducting circuits and topological qubits, to push quantum computing into the next stage of practical applications. The potential is enormous, from revolutionizing cryptography and drug discovery to solving complex problems in materials science and artificial intelligence.
And what about quantum cryptography? Is it true that it is unbreakable?
Yes, in theory, quantum cryptography is unbreakable. Quantum encryption uses entanglement to create ultra-secure communication channels. If someone tries to intercept the data, the quantum state collapses, instantly revealing the intrusion.
It's like something out of science fiction. Has it been tested?
It's already happening. The world's first quantum encrypted satellite, China's Mesius, has demonstrated ultra-secure communication using quantum key distribution, reducing the risk of interception. China is in fact reportedly preparing to launch a global quantum cryptography network by 2027.
So what's next? Where does all of this lead?
So, this season, we've explored the profound impact of quantum mechanics on our world, from the devices we use daily to the frontiers of scientific discovery. But this is just the beginning. We want to thank you, our listeners, for joining us on this journey into the quantum realm. Your curiosity and engagement are what fuel these discussions, and we invite you to be part of shaping where we go next. If you have questions, ideas, or topics you'd love to see explored in Season 2, write to us. Your insights might just help uncover the next big quantum mystery. In Season 2, we venture even deeper into the strangeness of quantum fields, the enigma of tunneling, the mind-bending reality of entanglement, and the future possibilities of quantum teleportation. If you thought this season was thrilling, we promise the next one to top this.
Quantum mechanics is only getting weirder and we're just getting started. See you in Season 2.